Okay, so next up is possible prior independent options. It's my pleasure to speak as well.
Thank you. Thank you very much for the introduction and for being here for this talk. Indeed, so here I'll be speaking about prior independent optimal auctions. So this is, we had a great introduction earlier, and this is joint work with Amine Allouah, who is a PhD student at Columbia University and who unfortunately couldn't be here today to deliver this talk, but he's really the driving force behind this work. Right, so again, in this audience, there's no need to motivate how widely used auctions are in practice and how relevant they are to a host of industries, and also how broad there is as a literature concerning all kinds of settings that try to address auctions and try to better understand auctions. What this talk will be about one fundamental assumption that is very often made in the context of auction design, namely that of common knowledge of the underlying distribution of the value of buyers, being the seller knowing this distribution and the buyers knowing the distributions associated with the value of other buyers. Right, on the one hand, making such a common knowledge assumptions allows for a very elegant formulation of the problem and for deriving very crisp insights about the possible structure of optimal mechanisms, but on the other hand, it might create a potential disconnect with practice where we might have limited information about how to construct such priors in the first place. Right, and even if we have a lot of data, the earlier talk showed that that data might be corrupted because of the incentives that people have to report truthfully along the way. Right, so what we want to try to understand is how can we relax this underlying assumption and what can we do about it, right? This is by no means a new question. This question was actually asked early on right after Meyerson's work, right, a few years afterwards. Wilson challenged this assumption of common knowledge and pushed for the need, basically, to find ways to relax this assumption, and at the core of this need, there are two, I would say, fundamental questions that we would like to address in this talk. One is really, how should we think about a prior independent optimal auctions? Right, and second, right, how close can we get? How much are we losing due to this prior independence? How close can we get to what we could have done had we known the underlying distribution? Right, and there is a stream of literature that has indeed tried to relax this common knowledge assumption, and we will be building on this stream of literature. Here, this is just a sample of the related literature, but I'll refer in much more detail to two papers that we relate closely to when I describe our results. Right, so let me first set up the model and the exact mathematical formulation that we'll be after before describing our result and our approach. Right, so what we'll be interested in is to try to understand in the most basic canonical model of a seller trying to sell one indivisible good to K buyers, and we will be assuming that there are at least two buyers. Right, so there are at least some competition in the market, and here buyers' values will be private, identically and independently distributed. Right, and the values will be drawn from some distribution F. However, the seller will not be assumed to know this distribution F, nor know the number of buyers that will appear in the market. Right, so this is what we're interested in. Now, what will the seller be optimizing over? The set of strategies that we will focus on are mechanisms that are summarized by the allocation and payment vectors that will satisfy these three conditions, namely these mechanisms should be mechanisms such that every buyer is willing to participate independently of the value of the other buyers in the market. Every buyer is willing to be truthful independently of the values of the other buyers in the market, and the seller can allocate at most one good. Right, and this are typically referred to as DSIC mechanisms, dominant strategy incentive compatible mechanisms. Right, so we'll refer to M as this class of mechanisms, and I'll add to that a technical assumption that these mechanisms need to be locally well behaved around zero. Right, and this will be the broad set of mechanisms that we're interested in, and over which the seller will be optimizing. Now, when picking such a mechanism, what's the seller's expected revenues? It's nothing else but the expectation taken with respect to the underlying true distribution F of the revenues collected over all the buyers. However, here the seller does not know F. As a result, he cannot evaluate such an objective, so we need a way to model that, right? One possible way is to take a robust approach, where we would take a worst case over this expectation. Another way is to introduce a benchmark. Right? And here we will take this benchmark approach where we'll compare what the seller generates to what he could have generated had he known the underlying distribution of values. Right? In particular, opt-F here will be the best possible mechanisms in the class M that could have been generated with the knowledge of the distribution F. And we'll measure the performance of a particular mechanism M by the ratio of what the seller generates versus what he could have generated had he known the underlying distribution F. Right? And here we'll ensure that this objective is well defined, so we'll focus on the general class of distributions CDF such that the expectation of F is strictly positive. And the objective of the seller mathematically will be the following, right? The seller will be trying to select a mechanism among this class of DSIC mechanisms, and nature may counter these mechanisms with any number of buyers greater or equal than 2, and any distribution drawn from a subset F. Right? So now we can define a family of max-min ratios that depends on the underlying class F that we select. Right? And what we can ask is, what is the best that the seller can do when being free to select among all these mechanisms, when nature may counter this mechanism with any distribution in this class script F, right? And here, just as a prelude, I mean, our results actually imply that the worst case is achieved exactly for k is equal to 2. So as we go forward in the talk, let's just assume that k is equal to 2, right? So what are subclasses of the class G that we'll consider? The first subclass is this class of regular distributions. If we only assume that the distribution is regular, what can be said? And another subclass, which is a subclass of the set of regular distributions that is commonly also used and assumed in the literature, is the class of monotone, non-decreasing hazard rate functions. Right? And we'll focus on these two subclasses. We know that the class of MHR distribution is included in the class of regular distribution is included in the general class, so we have this ordering in terms of the max-min ratio. Right? The worst max-min ratio is when nature has the most flexibility, then the case of regular distribution is in between, and then we have the best possible scenario if we are in the case MHR here. Right, and our objective in this talk is to try to pin down these different quantities and understand what is this maximum performance, and to what extent can we characterize what an optimal mechanism is for these different classes. Right? So let me now present our main results and the approach we take to derive these. So again, what we're interested in is to understand this max-min ratio as a function of the underlying class of distributions that we may face. Right? If we face general distributions, I mean, nature has a lot of power. It's easy to see that actually no mechanism among the class of DSIC mechanisms can guarantee a positive fraction of revenues. Right? So there's nothing fundamental there, but this gives us a benchmark of what happens in general distributions. Now the question is, what happens in regular distributions? Right? In regular distributions, there are already results that exist in the literature. As a matter of fact, we know that the max-min ratio is lower bounded by 51.2%. As a matter of fact, you know, the early result of Bullen, Klemperer, and the reinterpretations by Dagwan, Notai et al. Actually have shown that the second price auction without reserve price actually guarantees a fraction of 50% of revenues. Right? So we have a natural lower bound of 50%. And actually, recently, Fu et al. Established that you can do better than 50% if you randomize, actually by properly randomizing between the second price auction and inflating the second value, you can actually go beyond this 50% and reach 51.2%. In other words, here, when you want to counter nature, you may want to randomize appropriately, and that gives you significant power. Right? So here, what we have is a statement of feasibility. We know that we can do better than 50%, but we do not know how much could we do if we look at arbitrary mechanisms in this class of DSIC mechanisms. And so in our work will try to understand what's a fundamental lower bound on performance. Right? So first of all, we improve slightly this, we refine slightly this result, but really the main result is an impossibility result. There's no mechanism in this class script M that I can actually generate more than 55.6% in terms of performance. right? So among all of these mechanisms, there exists no mechanism that will be able to pass this performance. So in other words, we have characterized this max-min ratio within an interval of less than 4%. Right now, for the class of MHR distribution, actually corollaries of existing results can show that actually you can achieve at least 61.2%, actually corollaries of the Fu et al. Results. But, so what we established is that actually you can do better. You can actually achieve up to 71.53%. There exist mechanisms that yield this performance. But what you also achieve is a fundamental upper bound on performance, which is exactly 71.53%. Right? In other words, for MHR distribution, we characterized exactly this max-min ratio, and we characterize exactly also the saddle point associated with this problem. Right? So what are the implications of these results? The first implication, in MHR class, the optimal mechanism is actually a second price auction. Right? So randomization does not help against MHR distributions. The exact optimal mechanism is a second price auction. In the case of regular distribution, the upper bound here implies that we knew that the second price auction yields 50%. It's at most within 5.6% of optimal. Right? So a second price auction is also near optimal for regular distributions. In particular, these results tell us also that in these low information environments, like the ones we are studying here in these prior-free environments, there's a very weak trade-off between revenue optimization and efficiency. Right? So for MHR distribution, an efficient mechanism is actually optimal from a revenue optimization perspective. And in the regular case, an efficient mechanism is actually near optimal from a revenue optimization perspective. Right? So let me just detail a bit now how we approach these results and how we derive these results. Right? So at the heart of it, we're interested in this object here, which with the max-min ratio, where we are optimizing over the class of mechanisms, and nature is picking any possible distribution in this class script F. Right? And what's challenging here, a priori, is that we are optimizing over a class of mappings, essentially measurable mappings from reports to allocations and payments, and this is an infinite dimensional space a priori. And similarly, nature is optimizing over a set of distribution which is infinite dimensional. Right? We want to get a bit more handle on these different spaces. So the way we approach this problem is to actually have reductions from the space of mechanisms and from the space of distributions. Right? In terms of the space of mechanisms, the first thing that we establish is that we can focus without loss of optimality on scale-free mechanisms. In other words, we can focus without loss of optimality on mechanisms that would allocate in the same way if they observe values of 10 and 20 or 1 and 2. Right? And this is quite intuitive. In a prior-free environment, if my mechanism is somehow fine-tuned to a particular scale, nature could counter such a mechanism. Right? But this buys us quite a bit because now, if you think about it, for two buyers, I had earlier an allocation that depends on two values. Now suddenly it depends only on the ratio of values. Right? So now we can leverage this to actually establish that without loss of optimality, we can focus on mechanisms that are appropriate discretizations of an arbitrary mechanism. So we can actually think about the problem in a discrete fashion, and we can represent mechanisms as a finite collection of discrete thresholds and probabilities associated with these thresholds. Right? And this underlying steps allows us to have more handle on the performance of mechanisms and how we can analyze these. Now, on the space of distribution side, again, a priori focusing on all distributions at the same time, it's not clear how we can approach it, but what we introduce is one-dimensional near worst-case families that are fine-tuned to the underlying classes of distribution that we face, regular versus MHR. And the advantage that these give, first of all, they reduce the dimension of the space of distribution that we face, but they also allow us to simplify the space of mechanisms that we need to analyze. Under these near worst case families, actually, what one can show is that we never want to allocate to the minimum value, which allows to significantly simplify the set of mechanisms that we focus on. And looking at these all together leads to upper bounds on the underlying max-min ratio that we want, that are parametric upper bounds. right? These are upper bounds that are parametrized by the underlying optimal quantile associated with these nearest worst case families and these discrete thresholds, right? But they also give rise naturally to candidate mechanisms that could have good performance if they perform well against these near worst case families. These candidate mechanisms, we can analyze their worst case performance through a classical quantile analysis, right? So now, let me give you an illustration of the types of results that we obtain for MHR distributions through this generic framework, right? So for MHR distributions, one can establish that the max-mean ratio is actually upper bounded by this exact expression, right, which is parametrized by a single quantity, which is this optimal quantile corresponding to this near worst case family, right? And what's this, and the idea here, the key idea is that we know that under this scale-free discretized threshold mechanisms, right, we don't need to allocate to the minimum. So now we only need to care about whether we will ever want to allocate to the maximum or not. But what we can show is that the MHR structure, what the MHR structure buys us, is actually under this class of near worst case families, we never want to inflate the second value, right? So we never want to deviate actually from a second price auction under this particular class, right? And in some sense, this is really where MHRs are different, is that, there's much less variability associated with MHR, so we don't try to chase essentially the tail associated with these distributions. And as a result, we can essentially get rid of all of the thresholds for MHR distributions. And we have just one bound that depends just on one parameter. But this naturally gives rise to a candidate mechanism for MHR distributions, namely a second price auction, right? Because it dominates all mechanisms under a subset of these distributions. Why not try to establish what lower bound we can achieve for second price auctions? Actually, we can establish for a second price auction, the worst case performance of a second price auction is exactly the expression that we obtained for the upper bound, right? And at the heart of this, the argument is really based on a single crossing property associated with MHR distributions that goes back to reliability theory. Actually, there's a beautiful textbook from 1975 that analyzes actually MHR. In reliability, these are typically referred to as IFR distributions. And this single crossing properties allows to have an extreme case of MHR distributions which is an exponential distribution, and then combine this by analyzing the revenue, essentially the revenue functions in the quantile space. Right, and this gives rise to one of our main results, namely that the characterization of the saddle point for MHR distributions, given that I face MHR distributions, my optimal mechanism is exactly a second price auction, and the worst case performance that I will face is given essentially in closed form exactly by this expression, which is roughly 71.53%. So on this, let me conclude, right? And at a high level, what we've tried to do here is to try to better understand how we can formulate the optimization of or mechanism design in contexts where we don't know the underlying distributions. And we have done so by trying to introduce this max-mean ratio for different classes of distributions. What we have shown is actually that the second price auction is actually near optimal against regular distribution and exactly optimal against MHR distributions. And as a result, there is a very weak trade-off between revenue optimization and efficiencies in these environments. Of course, this raises many other questions that one may ask. In particular, what happens when we endow the decision makers with limited information about these distributions or about the particular number of buyers? One can derive sharper bounds that depend on the number of buyers, and trying to understand how this max-min ratio depends on the number of buyers, or potentially how can one refine this bound as we endow the decision maker with past observations of values of bids that we have observed. Right. On this, I'll conclude here, and I'll be happy to take any questions. Yeah. Yeah. So there are two questions. So indeed, you could put a minimum of k buyers, right? And indeed, we know that the max-min ratio will increase there. Actually, the Buller-Klemperer results imply that you have a natural lower bound, right, of n minus 1, k minus 1 over k, that will increase. Now, whether we can improve that to say that the worst case would be exactly at k, that's what you're asking?
So I was just asking for temperature.
Yeah. Whether second price optimal, yeah, so I would conjecture that this might be true, but I cannot claim that this is true at all, right? I don't know for a fact that this would be true. Actually, we leverage quite a bit the structure of two buyers here to be able to have this reduction, right? And this is what allows to have this natural reduction to discrete threshold mechanisms, but it's a great question, and it's a great open question. Yeah.
Some more questions? Kind of a naive question.
Yep.
So about unreal questions about how to record information, but how is that different from just, this additional information, how is it different from getting prior? How is it different from just saying, oh, you have this additional information, which means you have a prior?
So how is it different? Yeah, so if I say that, let's say I have, so it is different in the sense that I may have only a few observations of past values. If I have 10 observations of past values, I expect that I can do better, but how much better? Right, in some sense, we know what happens at the extreme when I have a lot of samples. When S is very large and I have a very large number of samples, we know what are the rates at which I approach the optimal. We know here where we are when we have 0 samples, but there is a whole curve in between. Right, and the question is how do we connect one to the other is an open question, and yeah.
Okay, listen, speaker.
Thank you.